Hello, I'm Philip Muggleston, and in this series of videos we're covering the predictive capabilities native to SAP HANA. In this and the next few videos we'll continue our look at classification by focusing on regression. Regression is one of the most widely used and popular algorithms in all of predictive analysis. Regression analysis involves building a statistical model that attempts to show the relationship between two or more variables through an equation. That model can be visualized with a line which is drawn over a set of data points and which most closely fits the overall shape of the data. So if we were to draw an example model, we might have here at the bottom we have income, and on the response we have spend. So how much people earn and how much they spend, and we have some data. We have a data set with maybe a large number or a small number of actual data points there. And then we use regression to draw a line through the data which most closely represents it. Regression shows the extent to which changes in a response or dependent variable, which is on the x-axis, can be attributed to changes in an explanatory or an independent variable which is placed on the x-axis. So for example, if the value of income is here, we can go up to where our line is drawn, and that will allow us to then predict what the relative value of spend would be for that income. Many types of regression exist, and the predictive analysis library in SAP HANA supports quite a number of them. For example, in this first case we were seeing a straight line, and that's what's known as linear regression, because the line is linear or straight. However, there are other types of regression, such as, for example, geometric regression, and in the case of geometric what we see is more of a curve, so perhaps a power curve looking like that. And there's also natural logarithmic regression, which is similar except maybe a slightly more aggressive curve. Also, we can see something which is known as exponential regression, which is where the curve fit maybe looks something a bit more like this. That would be exponential. And another type is what's known as polynomial regression. And in that case, we may have actually more of a wavy line or curve that represents the data. So these are the different types, but the approach is basically the same in all of them. If we have a value, for example, for income, we use that to then look at the corresponding or predicted value that we would have for spend. What we see here is an example where we have a single independent or explanatory variable which results in the dependent variable of spend. This is what's known as bivariate or simple regression, because we're just dealing with one single explanatory variable. However, it may be that we have a combination. We may have income as well as age and gender, all as being explanatory variables, which we could then use the combination of these three to more accurately predict what the future spend would be. Now obviously I can't draw a four-dimensional diagram here on the screen, but statistically and mathematically that's absolutely possible to build within our model. An important aspect is determining how useful the model is. Effectively, how good is the fit? For example, if we were to draw this linear regression line, how well does that fit? Effectively, we get something what's known as the R squared, which gives us an indication of how closely the data points we have in our source data, in our data set, actually fit. So it gives effectively the overall variation from each individual data point from the actual regression line. So here we can see some are close, some are further. Now R squared is typically between 0 and 1. So an R squared of 1 would mean that in fact all of our data points fit directly on the line. That's very unusual, but that would give us a very high confidence that the model is going to be useful. In the real world, what we typically see is a value somewhere between 0 and 1, which gives us an idea of that variance. However, the R squared value in itself is not enough in really determining how significant this model is. So we should not rely on R2 itself to determine usefulness. We have something else which is known as the F value. And the F value takes into account the size of the sample, how much data, how many data points we have, and also the number of independent or explanatory variables that we're working with. And F will provide us the statistical significance of our fit. And what we need to do is then interpret that F value in the context of what a statistician would refer to the F distribution. And if we find our value is in the 95th percentile, we can regard our model as being significant. If it's within the 99th percentile, it could be regarded as being very significant, probably something we can work with quite confidently. Two steps are required when we're working with this in the predictive analysis library of HANA. The first step is that we need to build a model. So we need to take this data and build out the model, which effectively will build our equation for calculating future or predicting future spend. And the second step is then to use that model to actually predict future values. So, for example, if we're looking at a new value of income here, to actually work out where would that fit in terms of spend. And it would use the line we've got in order to do that. In the upcoming videos, we'll go over each PAL algorithm that supports regression, and we'll see how they work in much more detail.